Hi all, welcome to the second part of the video lecture on transaction management. The first part of the video, we discussed the basics terminologies related to transaction, and also we saw what are all the possible issues that can happen when you allow concurrent execution of different transactions. So like lost update, incorrect summary problem, like that some of the issues we discussed. Now in this video we will see the solutions. Okay. Right, how we can so what is a valid execution of a concurrent schedule, or how we can control the concurrent execution of different transaction. So basically we have a terminology called schedule or history of transactions. So that is nothing but an ordering among different transactions, so how we are executing different operations. So some examples we already saw in our previous video. So a schedule or a history denoted by capital S of n transaction T1, T2, T3, etc. Tn is an ordering of the operations of the transaction. So T1 is having some set of operation, T2 is having another set of operation, and T3 like that. Now we have to order them in a particular way, right? Something like this. So here I have two transaction T1 and T2, and this is the order of operation, because first I am executing these two operations from T1, then these two operations from T2. So this is one ordering. Similarly I can think about another ordering, right? So this is basically what we call as a schedule. And you can think about such an ordering among some n transactions even. Now you have to keep this in mind, like whenever within a transaction Ti, the operations must appear in the same order in which they occur in the transaction. So the order in which set of operations are occurring within a transaction, you are not supposed to change when you are making a schedule. In the sense here, these are all the operations in T1, and they should occur in order, like after read x you can modify x, then you have to write x, then again you are reading y, and you are not supposed to do this read y before and this read x or something. Within a transaction you are not supposed to change the order in which the operations are occurring, but all together first let T1 proceed, then T2 proceed, then may T3 proceed. Like that you can have an ordering among the operations within between transaction. But within a transaction you are not supposed to change the order in which the operations are occurring. If you are changing the order, definitely that is going to result in a different transaction. It is not going to give you the same result like what we are expecting, right? Yeah, that about it. So that you can keep in mind. So, and you can see that the within a schedule the operations are having some kind of total ordering, in the sense any two operations in a schedule one must occur before other, and that ordering, because in the vertical line, or in the y axis we are taking this time, right? So with respect to time we are defining this is to be done first, then this. So that ordering is something known to be total ordering. We are not supposed to change this ordering. Okay, that is completely defined among all operations of all transactions. Now, for the purpose of recovery and concurrency control, we are mainly interested in the read and write operations, even though the transaction is modifying also, but we will focus mainly on read as well as write. In between, it is expected to have some modification. Okay, but we will focus these two operations, as well as the commit as well as abort. Sometimes it may abort and commit, that also you have to take care. And accordingly, there is a shorthand notation by which we can describe schedule, where we use BR, small letter BR, W, E, C and A for the operation. Say B for begin, okay, begin transaction. R for read an item as part of a particular transaction, and write, W for write operation, E for end particular transaction, and successful completion and changes are made permanent by an operation called a commit, and in between if there is any failure we have this abort operation, that is denoted by A, commit denoted by C. Okay, like that respectively, and appends a as a subscript the schedule transaction ID. So something like B suffix 1 along with this this particular letter B, R, W, etc. We typically suffix a number, say R1, that says that the read operation is happening in a transaction T1. Okay, this one says that it is transaction 1, and to each student here, and in bracket that's this last one, the data item x that is to be read or written follows this r and w operation in parenthesis. For example, I want to read the data item x a part of transaction 1, I'll be denoting like this, r1 of x. Okay, similarly, if I want to write an item as part of transaction number 2, say I want to update write this particular variable y, I can write like this. Okay, so typically we will use this kind of b r w e c a. Okay, this letters corresponds to begin, read, begin transaction, read, write operations, then end transaction, commit and abort, and this number says that in which transaction it is happening, and in bracket we will mention the item if some item is involved, particularly for read as well as write. So for example, here you can see a transaction and how this schedule is written. This particular schedule 1, which is an interleaving among transaction, is written. So we are just focusing on the major operation, that is read operation. So I can say that first it is the read operation happening in transaction 1 on an item x, right, followed by the next one is some update, but we will not hide update, read as only and write only we will write in the final schedule. Okay, similarly then read is happening in transaction number 2 on the item x. Okay, followed by after that, so this is the second operation, we are taking timeline. Okay, accordingly you are writing, there is a write operation that is happening in transaction 1 on the item x, followed by I have a read operation that also happening in transaction number 1 on item y. Okay, then followed by I have the write operation w1, I mean w2 on transaction number 2, okay, on an item x, followed by I have a write operation on transaction number 1 on item y. So this is a shorthand notation for the given transaction. We can represent like this. We are just focusing on the read and write operation, and of course if there is commit and abort, that also you can denote by, if I written like commit or something, some c, like that we will write. Okay, so sometimes the schedule will be given like this, and once the schedule is given like this, you should be able to write the schedule like this, and you can see if it is violating any or whether it is creating any issue because of this non-serial execution. Those analysis you can do further once you have this kind of a notation. Okay, but this is another shorthand notation we are having. This is another example. Here read on transaction 1 on item x is happening first, then write on transaction 1 on item x, then read at a transaction 2 on item x, write 2 on x. So this is actually a suffix. So okay, it's come like a subscript. Okay, so that's a correct notation, or you can write like this also. Anyway, you have to mention the transaction number as well as the item on which that operation is done. As here there is an abort operation also that is happening in I think you remember this example. After this particular transaction aborted, and accordingly some temporary update made by this one is lost. Okay, so temporary update problem like that we studied, that time we taken this example. That is why this abort is happening at transaction 1. Okay, yeah, that about it. Now let's focus on something called as conflicting operation in a schedule. Conflicting in the sense by some way the order changes, you know, some unexpected result will occur, and particularly the operation the problems like lost update, incorrect summary, the temporary update, those problems are basically because of these conflicting operations that are not executed in the right order. Okay, so that is crucial for us. Let's define what it is. So two operations in a schedule are said to conflict if they satisfy all of the three conditions. So first thing, I am talking about the operations in different transactions, right? Two different operations I am focusing as part of a schedule, and I am saying that these operations are conflicting first of all. Okay, so I am just focusing on two operations of the schedule only. But when I can say that it is conflicting, first thing, they should belong to different transaction, and you are talking about say two operations. So here this read and this read you are talking, and you are not supposed to say that it is conflicting. First of all, this one should be here and this one should be here. They should occur in two different transactions. So that is the first criteria. Second criteria is they access the same item x. That also you have to ensure they access the same item x, and then at least one of the operations should be a write operation. Okay, write x. So can you tell me on conflicting operation here? The first requirement is like they should happen in two different operation. Sorry, these operations should occur in two different transactions. So let me focus on this read x and let me find out is there any operation conflicting with it. So you don't have to look at any operation that is happening inside a T1 because within a transaction the operations are not going to conflict at all because they will execute in a sequential serial manner only. The order is not going to be violated. Now, if you look at T2, can you identify on conflicting operations? So, first of all, they should be on two different transactions. That criteria is okay. Now, what is the second criteria? Second criteria says that it should be on a common data item. So, you can focus here. This is X. So, you can focus on this operation or this operation and you can check to see whether it is conflicting. And the third property is one of the operations should be a write operation. Okay. So here in the first case, this is read x and this is read x. They are not going to be conflicted because both are read. We need one of the operation as write. So I can say that this operation and this operation are conflicting. Okay, so three conditions. The operation should occur in two different transactions. Right, when two operations are said to be conflicting, first thing they should be in two different transactions. Here it is so, right, T1 and T2. And they should happen on a common data item. Here both are updating or reading that particular operation is happening on a data item X. And the one of the operations should be write. Here read and write. Okay, fine. So write, all are fine. And accordingly, two operations are conflicting if changing their order is going to give you some unexpected result. Okay, so that should not happen. And accordingly, we have a read-write conflict. So as well as write-write conflict. Here you can say this is a conflicting, particularly this is read and this is write. I can call it as a read-write conflict. Okay, and you can think about something called as write-write conflict also. So our requirement is like one of the operations should be write-write. See, it is here only, but at any time we need to see whether any one of the operation is conflicting. That itself says that this is not a correct schedule. Okay, we are not supposed to. So here write on x, here also write on x. I can say that it is write-write conflict. So because of this conflict, actually we are facing with those problems that we discussed so far, and we are trying to avoid this. This is what is basically happening in something called a serialization. Okay, we will see that. Characterizing schedules based on serializability. Okay, so you understood what is a schedule and what about the conflicting operations within a schedule. Now let's see whether a schedule is serial or not. That is the first thing we have to discuss. What is a serial schedule, like that. Then if it is not a serial schedule, it may happen like because of the serial if it is not a serial schedule, definitely because of the influence of conflicting operation. Now how we can deal with them, so that is the question. So how we can the topic discussed is how we can characterize different schedules based on their ability to serialize, even though it is a non-serial schedule, whether they are equivalent to some serial schedule. Okay, whether they are serializable. So that is a topic. Okay, so let's see. We can basically classify schedules into two categories: serial schedule and a non-serial schedule. That is the first thing. What is a serial schedule? Something we already seen. If I have n transaction, one transaction can start only after the currently being executed transaction is completed. Okay, you take each transaction in any order and let the transaction finish completely and commit, then only you will allow any other transaction to start. That can happen randomly. But once the transaction started executing, it is supposed to finish and commit, then only another transaction can start working. If you are maintaining that order, I can see that particular schedule is a serial schedule. So what is a serial schedule? If for every transaction T which is part of this particular schedule, all the operations of T are executed consecutively in the schedule, otherwise that is another way to say one schedule should be finished completely and then another should start, or all operations of a particular schedule should occur consecutively. That means in between you are not interleaving. Okay, so one after another all operations within a schedule is happening consecutively, means in between it is not interleaved by some other operations. So that ordering is maintained. Okay, clear. Otherwise I can call it as a non-serial schedule. Therefore, in a serial schedule, only one transaction is active at any time, because I want all its operation to happen consecutively. So only one transaction is active at any time. After the commit of the current transaction, I will initiate another one. The commit or the abort of the active transaction initiates the execution of a new transaction. And there is no interleaving at all. Okay, you are not supposed to take on transaction while the other one is executed. That is not possible. Now, so typically, most of the time what we need is non-serial schedule, because serial schedule, if there are 1,000 transaction, what about the last transaction? It has to wait for all the 999 transaction to finish. So it is something not at all be recommended for any application, particularly for this railway reservation or that kind of application where that concurrency is a must. Okay, so in that case we can have this non-serial schedule for sure. And but can you tell me how many serial schedules are possible? If I have a n transaction, I can arrange this transaction in n factorial ways. Just like suppose I have 3 transaction, one serial execution is T1 followed by T2 followed by T3, and another serial execution possibly say you can start with the T2, because we don't have any dependency between them, but we want them to execute one after another. Say T1 T2 first, then T1, then T3, or T1 itself. Here I can change the T3 first, then T2. Okay, like that, some 3 elements can be arranged in 3 factorial ways. This is on arrangement, right? T1, T2, T3, then T2, T1, T3, T1, T3, T2. So like that I can have a 3 factorial, that is equal to 6 schedules are possible. 6 serial schedules are possible. Here each one is a serial schedule, right? Fine. So n transactions I can arrange in n factorial ways. So each one is going to be a serial schedule. But now tell me, what about non-serial schedule? Within a transaction itself, we are enabling that interleaving, right? From one transaction, I am moving on to another one. Again, I am coming back to this, or a third one. Like that, when I am proceeding, the number of serial schedules is a much bigger number, right? It's not. It's at least n factorial. It is a very big number. Now, out of that many possibility, how can I pick the correct possibility? That is the question. We all want the concurrent execution of schedules. I mean, the transaction should be executed concurrently. That is only required by the user. Okay, for most of the applications. We don't want this serial schedule. We need this non-serial execution, and that time you are not supposed to allow all non-serial execution, because we saw many non-serial execution and the problems associated with them. See, you have to ensure that given any non-serial schedule, can it allow it to execute or not. You can allow it to execute if it is not going to create any problems like a lost update or temporary update or incorrect summary. Those problems will not be there, provided you are going to allow this non-serial schedule in a particular order. Typically, what kind of non-serial schedule you can allow, and they are those which can be serializable. Okay, if a non-serial schedule is equivalent to some serial schedule, and the transformation process is what we call as serialization. A non-serial schedule you can map to a serial schedule. We will see how this mapping is done. So if I can find a serial order, even though the schedule is non-serial, or the non-serial schedule I can execute in a serial manner, or the result given by the non-serial as well as some serial schedule, they are same. If that is the case, I can say that the non-serial schedule is serializable to some equivalent serial schedule. Anyway, if you have any doubt, we will see example and we will be very much clear about it. And accordingly, you can think about 2 disjoint groups of non-serial schedule. Serial schedule itself, if I have n transaction, n factorial serial schedules are there. So the number of non-serial schedules is much higher, and that I am partitioning into 2 disjoint group. Partitioning, there is no overlapping, and when you take the union, you will get the whole set of non-serial schedule. And the first partition is going to contain all non-serial schedules which are equivalent to some serial schedule, okay, and which are hence serializable. And if a particular transaction schedule is not serializable, you can put it in a different group and call that these are all the non-serial executions which are not serializable at all, so it is not good to proceed with them like that. So okay, now what we need is a given any non-serial schedule, you have to ensure that it is equivalent to some serial schedule. And what kind of equivalence one can think about, one popular measure is conflict equivalent, because when you look at the conflicting operation without any violation of their order, you can achieve the execution possible. If the conflicting operations, if you change the order, definitely the answer will not be what you are expecting, okay. So you have to ensure that all conflicting operations are executed in that order, and in that way, given any non-serial schedule, if it is if I can convert that into a serial schedule, okay, if I can say that this particular non-serial schedule is equivalent to some serial schedule, one way I can say that statement is with respect to conflict serializability, okay. That mapping process what we call as serialization process, and here we can do it by focusing on the conflicting operation, okay. So accordingly we can say that whether a given non-serial schedule is conflict equivalent to some serial schedule, okay. And we will see what it is with example, it will be very clear. And for those doing this conflict equivalence checking, we typically draw a graph called a precedence graph or a serialization graph, by which we are going to convert our non-serial schedule to equivalent serial schedule. Convert in the sense for our understanding as well as analysis we are converting, and we will verify that this non-serial schedule is valid and you can allow, so that the database will allow such serial schedules. But we have to ensure that the once that non-serial schedule is being executed, it should not create any unexpected or unwanted result, okay. Accordingly we draw the serialization or precedence graph where each vertex or node corresponds to a particular transaction, okay. And there you can think about different edges between them, how these edges are being drawn we will see with our algorithm, okay. So this is the algorithm, it's a very simple algorithm. Let me quickly read it, and I will take an example and explain to you. That is good actually. So basically, you know, each transaction corresponds to a vertex in the precedence graph, and then we will focus on the conflicting operations. Say read on X in a particular transaction Tj followed by after. So first thing happening is on transaction Ti I have a write operation, followed by I have a read operation on transaction Tj. So I can just represent like Tj is actually following Ti, okay. So that you can represent by an edge. So the vertices are nothing but the transactions of the given schedule, and edges are going say from Ti to Tj, provided I have a conflicting operation in Ti, and that operation is conflicting in the sense it is conflicting with another operation is Tj following this Ti's operation. So okay, I will take an example and explain to you. Accordingly I can have an edge from Ti to Tj, and there are other situations also. We will take example and explain, okay. These are all examples given, but I think we will take a problem that is being asked in GATE, and with the help of this problem I will explain you clearly how this serialization checking can be done, okay. So this is something asked in GATE 2022, so recent GATE question, and let's see how it can be solved. So while explaining this example, I'll explain that algorithm on the background. So after seeing this example, we will go back to the theory part. Okay, so just focus on the question. So let Ri of Z and Wi of Z denote the read and write on a data element Z. Okay, so this notation is something familiar for you, right? So R, so I think in our explanation we used a small letter, but okay, in the question it is given like capital R for read and W for write. And the transaction number is I. On the ith transaction we will denote like Ri, R suffix I, okay, or subscript like that, okay, I. If it is also R4 here means the read happening on 4th transaction, on second transaction, like that. And this is a data item on which you are performing the operation. Okay, here it is insert, here it is data item X is read by transaction number 4. Here it means data item X is read by transaction number 2. After that, data item X is read by transaction number 3 also, like that. Then like that operations are coming, and you are supposed to consider this particular schedule of 4 transactions. So this is given, and which of the following serial schedule is conflict equivalent to the given schedules. The given schedule, as it says, we are interleaving, right? First I am executing this read operation from transaction number 4, then transaction number 2 I am coming, I am allowing this read operation, then I am moving on to transaction number 3 where I am allowing this read, then transaction number 1 I am coming back, this read, not coming back, I am first time exploring transaction 1, then transaction 1 itself I am proceeding with this write operation, then transaction 2 I am moving and write X, like that it is happening. Okay, so what and it is so, what I was trying to say, this is a non-serial schedule, right? It is a concurrent execution. So it is a non-serial schedule, and if it is a non-serial schedule, one can ask about, so what is given is a non-serial schedule. Is it a valid non-serial schedule, right? Is it good to allow this without any, when you, while executing this particular transaction, will it creates any problem like we discussed, like lost update, incurrent summary or temporary update? Is there any chance of such problem? If nothing is there, I can say that it is I can allow, right? So you can allow a non-serial schedule provided it is equivalent to some serial execution of the 4 transaction. So these are all some of the serial executions possible. So here this first option says that transaction 1 followed by, only after completing each and every steps of transaction 1 and after committing it, I am moving on to transaction number 3. Again, after committing transaction number 3 fully, I am moving on to transaction number 4. This is one of the serial execution. Here I am starting with the T1, then I am moving on to T4. This is another one. Here I am starting with the T4. So these are all different serial executions, right? These are all. So can you tell me how many such serial executions are actually possible? If there are n transactions, n factorial serial schedules are possible. Here I have 4 transactions, so 4 factorial is equal to 24 serial schedules are possible, serial execution patterns are possible, and out of them some 4 options are given, and they are asking whether the given non-serial schedule is equivalent to any one of these 4 schedules given, okay, or any one of the 24 serial schedules possible. Anyway, as it is a gate question, out of the 4 options, one will be your answer, okay, so we can hope so. So what is given is a serial schedule. If it is equivalent to any out of 24, if this 4 schedule over 4 transaction is equivalent to any one of the serial schedule, I can say that this particular non-serial schedule is serializable. So the question is basically whether the schedule is serializable or not. Okay, so that is what we are asking. So serializable in the sense whether it is equivalent to any one of these 24 serial schedules possible. Okay, and that serializability checking itself you can done in a number of ways, and one possibility is by using the concept of conflicting operation. Accordingly, we are trying to see whether it is conflict serializable. Okay, conflict serializable. Now what do you mean by conflict serializable? The given the question is now like whether the given non-serial schedule equivalent to some serial schedule. So let me add the word whether the non-serial schedule is conflict equivalent to. So this word is important, conflict equivalent to some serial schedule. So this is basically I am asking when it comes to conflict serializability checking. Okay, so with respect to the conflicting operations, can I say that it is equivalent to some serial schedule? So that is what we are asking, and we will see how it can be approached. So what we are doing is like we are just looking at the schedule, non-serial schedule given, and it is interpreted in a way like with respect to you know this notation, right? In the order in which these transactions are happening, that you know, and that we are depicting in a different way, so that it is more easy for us to analyze than this. Okay, so what is done, there are 4 transactions, and along with this vertical line we have a time. Okay, so this is the timeline that says the order in which the individual operations of the transactions are being executed in this particular schedule. So you can see that it started with the read operation on transaction number 4. So this is being happened first, followed by a read operation on transaction number 2. Okay, then transaction number 3 read, then transaction number 1 write operation, sorry, read operation, transaction 1 itself write operation, transaction number 2 write operation, right, then 3 write operation. That is the order, followed by the transaction number 4 write operation, sorry, read operation, whatever it is, so that you can just map that given schedule into this form, right? This is clear, right? And then you have to see whether it is equivalent to conflict equivalent to some serial schedule. So how we can do this conflict serializability checking? Let me tell you the method. So just focus here. So what we have to do is we have to draw a graph called a precedence graph. So it's very straightforward. What you have to do is, how many transactions are there? T1 is a transaction, and T2 is another transaction, and we have a third transaction T3, and there is T4 also. And each transaction of the given schedule is going to be a vertex in the graph. So how graph, basically we have vertices and edges, right? Now what about the edges? So edges are going to focus on the conflicting operation. Now hope you remember what is a conflicting operation. First of all, it should occur in 2 different transactions, right? Some T1, T2, or some 2 different transactions Ti and Tj, and within a transaction I am talking 2 operation, and I am saying that conflicting, that is meaningless. So conflicting operation means they should occur in 2 different transactions. Second thing, what was it? It is like one of the operations should be the write operation, right? Hope you remember. And also it should be on a common data item. I think 3 points we discussed. It should happen in 2 different transactions. Then on a common data item, that was second point. And the third criteria is one of the operations should be a write operation. Then only I can say that these 2 operations are conflicting. Now if I have a conflicting operation and the order in which the operations are performed is like a transaction Ti followed by Tj, then accordingly I will have an edge from Ti to Tj. So that is the rule, that's all. So let me just tell you. So how to draw the graph. So I am starting with the transaction 1, and I am going to see whether any of the operations of transaction 1 is having a conflict with any operations of any other transaction. If that is the case, I will be having a edge from transaction 1 to that particular conflicting transaction with the conflicting operation, right? So let's see. So the first operation in transaction 1 is read on an item Y. Let's see whether this transaction 1 is conflicting with the transaction 2. So just focus on transaction 2. Following this, okay, no needed to look at the conflicting operation before this read. So you are going to see whether this read operation is conflicting with any operations in T2 following this time. Okay, so that is important. Don't look at anything before this. Okay, so from this point onwards, look downward, see whether the conflicting operation for read is right, whether any write is happening on the same data item, say Y. So nothing like that is happening, right? So I can say that there is no conflicting operation for the first operation, that is read Y. Now the second operation is write Y, and I am going to see whether there is any conflicting operation. Here is write conflict, you can see, but on a different data item, that is not a conflict at all. Okay, so here it is not a conflicting operation. So we can conclude that there is no conflicting operation between T1 and T2, and they are not going to have any edge. Okay, so if any one of the operation is conflicting from one transaction to another, I will have an edge from the first one to second one. Okay, now let's see whether transaction 1 is conflicting with the transaction 3. Yeah, here you can see you have to verify the set of operation T3 after this time. Okay, following this read Y. Okay, that is important. So here it is read Y, and you can see that the read operation on this particular transaction on an item Y, here we have the conflicting operation, right? Read write conflict we are having on the same data item Y, so it is a valid conflict. I can say that the transaction 1 and transaction 3 are conflicting on a data item. Let me use some different color initially for the explanation. This R of y and W of y, these are going to conflict each other. So accordingly, I can draw an edge. Transition number 4, right? So I can draw an edge from T1 to T3, and see there is no edge from T1 to T2, that we already verified, okay? But T1 and T3 conflicting on the data item y, with and the type of conflict we are having is read write conflict, okay? So I can say I have a read write conflict, and it is happening on an operation in T1 followed by an operation in T3. That's why the edge is going from T1 to T3. I'm not writing like that, otherwise you may misunderstand that there is labeling and all. There is no labeling needed, okay? So this is our graph. Now let's see whether T1 is conflicting with the T4. So focus on all operations on T1 following this timeline. There is only read by, and read is not going to conflict. So this is not a conflicting operation. That says T1 and T4 there is no edge at all, okay? Similarly, you can check for T2. This is the operation read x, and see whether it is conflicting. Following this operation, there is no conflicting operation on the same data item, right? So T1 and T2, there is no conflict with respect to R of x, and W of x also there is no conflict, because following this there is no operation in T2 at all, okay? So you don't have to check it. So T2 and T3, you can see here it is read on item x. Here it is read, it's not a conflict, and write and read, but on a different item, that also not going to conflict. So T2 and T3 there is no arrow, and Wx is here, but that also there is nothing conflicting following it, right? So T2 and T3 is okay. And what about T2 and T4? Here the data items are x. Here you can't see anything x following it, right? So there is no conflict between them. So that means T2 is something not being connected with others, right? It can be executed at any time, so it is not having any dependency with the other operation, okay? With other transactions. So now what about the T3? T3 R of x is here. Is there any conflict with the T1? Following it, there is nothing happening on x, okay? So there is no conflict between T3 and T1. And now what about T3 and yes, now we have a conflict. And is between this read operation R of x. Following this on T2, following this operation, I have this write on the same data item, read x, write x. So I have the read write conflict on the data item x between transaction T3 and T2, and you can see that the operation in T3 is conflicting with something following it. So the edge is going from T3 to T2. We can see this edge because of these two operations. Now similarly, between T3 and T4, is there any conflicting operation? Yeah, you can see this. With respect to this x, there is nothing conflicting, but with respect to this y, W of y, write operation and read on the same data, write to read on the same data. So I have a conflict from T3 to T4, because T4, that operation is following the corresponding operation T3. So I have an edge from T3 to T4. Now let's verify what about T4. If you are looking at a T4, this is on X read, there is no conflict with the T1, there is no X axis, right? So read here also no issue. But let me tell you, I got a conflict now, T4 and T2. This is on read on item X. Here I have read on write on the same item. Okay, so with respect to the data item X, I have a conflict between T4 and T2, and I have an edge from T4 to T2. So this drawing of the graph is very important, okay. Then similarly, this is read x. There may be multiple conflicting operation, but as soon as you are getting one pair, you can draw that edge and you can move on to the next checking, okay. Here it is R of x, okay, no conflict. Here it is R of y and no conflict. So between T4 and T3, there is no conflict, okay. And other things also we checked. See, this is a final graph you are getting. Okay, now it is very important. So this graph, what this graph is trying to convey, the graph says something like the conflict operations evaluation order, something like that. Here there is something conflicting between T1 and T3, that magenta, that edge is saying so. Something to be done in T3 should be executed after T1, but due to any reason, if it is happen, it can happen in a different order, it is going to give you a wrong evaluation, something like that. Okay, similarly, some dependency you can see between T3 and T2, and the order is from T3 to T2. So that kind of a graph you are getting. And if there is some cycle in the graph, what does it says? Something like, let me create a cycle here manually. Actually in the graph there is no cycle, so the cycle it is coming from T1, T3, T2, T1. Now it says that whether you execute in the order T1, T2, T3 or T2, T1, T3, all are going to give you the same result. In the sense, the actual ordering that we are expected to have is it's going to, I mean, in the original serial schedule we have the requirement like one should follow another one, that is not being met by this particular non-serial schedule. Okay, so that kind of interpretation it is having. So what we are doing is, actually we don't have this edge. Okay, so our algorithm is just over, and at the end you just see whether the precedence graph you are obtaining is having a cycle. Here you can see this like a cycle, but it is not a cycle in a direct graph, right? In a direct graph what we are expecting is a direct cycle. Here you can see from T3 I can reach T2, but from T2 you can't reach T4, so it's not going to create any cycle. Similarly T3 I can reach T4, and then I can reach T2, but there is no way to reach from T2 to T3, so there is no cycle actually. Okay, this is not a cycle, it's just a closed figure, but it is not a cycle when it comes to direct graph. So whenever there is no cycle, I can say that it is conflict serializable. Okay, so conflict serializability checking is over. I can say that this schedule is a valid schedule. You can allow this schedule, that it is not going to create any problem with respect to serializability. So it is going to ensure the final result equivalent to some serial schedule. Now we have to see what is that equivalent serial schedule. Okay, that is very much straightforward. Now when you are getting a graph like this, you are getting some kind of dependency between the conflicting operation between the transactions, right? So, and you can see that for the transaction T1 is something that can happen. I mean, it is not depending on the output of any other transaction, right? So you can start with the transaction T1, no issue. But can I start with the transaction T3? No, I can go to T3 only after finishing T1. Similarly, what about T2? I can reach T2 only after finishing T3, right? But to finish T3, I have to start with the T1. Like that it will go. Okay, so that is the meaning. So what basically we are doing, we can start with the T1, right? Then we can go to T3. This is the order I am getting, right? From T3, you know, I can reach T2 or T4. Suppose I am reaching T2. And after T2, this says that first I am executing T1 followed by T3 followed by T2. And then, you know, you can reach T4, because T4 the only requirement is it should be executed after T3. T3 already finished, right? So I can execute T4. So this is on valid schedule. And similarly T1, then T3, then suppose from T3 if you want you can reach T4 also, because that is just depending T3 to finish. Okay, then you can execute T2, no issue. So all these are valid answers. I think T1, T3, T4, T2. This is the correct answer with respect to the gate question they asked. So what is the problem here? Here after T1 I reached T4. That's not possible. You can reach T4 only after finishing T3. Right. Similarly here T4, I started with the T4. That's not possible. You can reach T4 only after finishing T3. Here in third one also I started with the T3. That is also wrong, because I am supposed to finish T1 before moving on to T3. So that is very important. Now you can see what we are actually doing is we are basically doing something which you might be familiar. So this how we listed this transaction, there is something called as topological sorting. If you don't know this terminology right now, you will see this in detail in your algorithm analysis and design course. So given any graph, how can I do this topological sorting? So first of all, topological sorting is applicable only for a directed acyclic graph. Okay, so a directed graph with no cycle. Okay, so that is very important. So as we got a directed acyclic graph, we can apply topological sorting. And in a topological sorting, we are basically listing vertices based on their order of application or evaluation or something like that. Okay, and let me just tell you one algorithm. If you want to implement, what you can do is you can start with a vertex node having 0 in degree. 0 in degree says that nobody is coming to this. Okay, so it is not following anyone, so you can just start from that vertex. So here the only vertex with the in degree, hope you remember what is in degree and out degree. Number of vertices coming, edges coming to a vertex is what we call as in degree. Number of edges going out is what we call as in degree, out degree. Here if you are looking at a T3, what is this in degree? In degree is 1 because only one vertex is coming to this. What about its out degree? 2 vertices are coming out of T3, so I can say that out degree is 2 and in degree is 1. So you understood the term, right? Now you can start a vertex with in degree 0 and you can print it. So here you can see that T1 is of in degree 0 and I am printing it. So always the starting vertex is T1 in our example because there is no other vertex with in degree 0. So once you output a particular vertex with in degree 0, remove that vertex as well as edge from the graph. There is nothing. Now you will get some other vertex of in degree 0. If it is a DAG, it will happen so. Okay, some other vertex of in degree 0. Here after removing this, you know, T3 is having in degree 0. Before that it is having in degree 1, but I removed that T1 as well as the outgoing edge, right? So T3 is having in degree 0 and out degree as 2. So you can start with the vertex having in degree 0 then. T3 is the next vertex you are going to visit or you are going to finish. Okay, so it's the next vertex in the topological sorting. You can interpret in a number of ways. So once you listed T3, you can remove that vertex as well as all the edges associated with it. Now what remains is this one, and here it says that sorry, I made a mistake actually. This is a wrong answer, right? This is a wrong answer. Why it is a wrong answer? Because there is one more dependency. This T2 is actually depending on T4 and T3 to finish. So only after finishing T4 and T3 I can move on to T2. Okay, so but for T4 I have a dependency with the T3. So after finishing T3 I can move on to T4. Then only I can go to T2. So that is important. So here what I listed is I started with the T1, then I moved to T3. From T3 I moved to T4. And from T4, sorry, this is a correct solution and this is a wrong solution because from T1 I reached T3, fine, but from T3 you can't reach T1, T2. So this is something that is happened wrongly because reaching T2 means you can reach T2 only after finishing T4. Sorry, I didn't see this edge. Okay, so that's why I made that mistake. Okay, now let me remove everything back. Okay, basically what we have is, let me remove this also because it may create some confusion on you. I simply written, but actually there also one of the arrangement is wrong. Okay, so here I think so far we have only, so it is going in a very systematic manner and we are having only one topological sorting possible because first I have to remove T1 as it is having in degree in degree 0, then after T3 will be having in degree 0, then correctly we are getting T4 as in degree 0, then it is T2's turn. So there is only one topological sorting possible for this particular conflict particular directed acyclic graph. So that is T1 followed by T3 followed by T4, then only you can come to T2. So this is very important. And that is going to be the equivalent conflict serial schedule conflicts. So what we done is a given non-serial schedule, we checked for conflict serializability and we saw that it is conflict serializability because the underlying precedence graph is not going to contain any cycle. And if that is the case, what is a equivalent conflict serializable schedule, right? What is a conflict equivalent schedule, something like that. And we saw that basically we are doing topological sorting of the given directed acyclic graph. Start with the vertex with the 0 in degree, then the next one. So we are basically listing vertices in the order in which they are to be evaluated. Okay, so this is how you got it. Yes, that's all. Hope you understand how to approach this kind of a problem. So this is something frequently happening in GATE. And here we have this algorithm. Now you can follow this algorithm easily, testing conflict serializability of a schedule. For each transaction participating in the schedule, create a node. So that is the first thing we done in drawing precedence graph. We created a node for each transaction. Now for each case in the given schedule such that I have a transaction Tj which executes a read item after Ti executes a write item. So the first operation is Ti is executing a write on an item X, followed by this I have a read item on the same data X, but done by Tj. So followed by, so Ta is happening first, right? So from Ti to Tj I have a edge. So this is the direction, that is from Ti to Tj. That is important. So it should happen on two different transactions, then on a common data item, that is X in both, and read and write. That's why. So and the conflict is happening first Ti, then Tj. Okay. Similarly, this is about read write. Similarly, write read is also going to create an issue. The write is happening in X after a read in Ti. So the third one is actually read write conflict. Second one is like a write read conflict, right? And the last one is write write. So both having write on a common data item, and they are conflicting each other, and accordingly we have this edge from Ti to Tj if the conflicting operation Ti is happening, followed by the conflicting operation in Tj. So okay, that's all. Now the schedule S is serializable. Particularly it is equivalent to a conflict serial conflicts. It is conflict equivalent to a serial schedule, or it is conflict serializable if and only if the precedence graph has no cycle. So this is very important. If and only, we have a formal proof also for the same, but we are not supposed to study as part of our UG course, okay? Like whatever, but anyway, hope you understand how that checking is done, how to draw the graph, and also how the graph, if there is no cycle, we are safe, right? We have a serializable schedule, and we are supposed to allow that schedule without making any issue. But if there is a cycle, it is not at all recommended, or it's not correct to proceed with that particular schedule. It is an invalid non-serial schedule. So if I am getting the underlying graph as something acyclic, I can say that it is a valid serial schedule, okay? Valid non-serial schedule because it is serializable to some serial schedule. Okay, so now these are all some examples taken from textbook, and here you can see this is our serial execution, T1 followed by T2. So in the corresponding precedence graph, I have T1, T2 as two vertices, and there is an edge from T1 to T2. Here T2 is started first, then T1. Okay, that's why the graph is coming like this. So this is how to draw the precedence graph for a serial schedule. This is just two or more vertices, and they will be connected like a chain. But now we have a non-serial schedule like this one and this one. Here I have an edge from T1 to T2. There might be some conflicting operation T1 and T2, read write. You can see read and write on the same data item X. That's why I have an edge from T1 to T2. Similarly, from T2 to T1 also, this is read and write. Again, I have a conflict. So I am getting a cycle. Says that this particular schedule, I think we already saw its problem in our previous video. It's going to create some issue. Don't allow this kind of a schedule. We will allow only those schedule for which the precedence graph is going to contain as no cycle. Okay, so only those transaction schedule we will allow. Similarly, what about this one? Even though it is in interleaving, you can see only edge is going from T1 to T2. But remember, in all these cases, this commit or about those things are not highlighted. If they are there, still you should be able to draw the graph. Because for the graph, we are only considering that read and write operation or the conflicting operation. That pairs only we are considering, and we are not looking at the other features. Okay. Yeah, this question, and I hope it is clear now. Yeah, thanks for watching. So similarly, you can expect even for your university question also some schedule will be given. You may be asked to find out or check whether it is conflict serializable. If it is conflict serializable, what is the equivalent serial schedule? Okay, like that questions will be coming. So it's a very important topic. Thanks for watching.